Hello, welcome everybody. This is the third session of the Points Topology to NPTEL course. My name is Shavik and I'm working on customer adventures. So, being is the third live session, before starting, let me know do you have any question or inquiries, or before that, let me know whether am I audible properly and is the screen visible to you. Please let me know. So there is one participant. Mustaq, can you please let me know whether I'm audible properly or and is the screen visible to you?
Yes, audible and screen is visible.
Okay, thank you. Okay, before starting, let me know do you have any question or a doubt regarding the last session? Please let me know.
No, no, you can continue.
Okay. So in that case, we shall start with hmm, what? Hmm, okay. So in that case, we shall start with solving problems. So let me figure out my Moncrief's book. Hold a moment, please. Okay. Last in the last session we have done things regarding the countability axiom mostly. So and also so we have done both countability axiom and separation axiom in the last session. So and we have we have exploited that why the countability and separability these things are necessary. The point is that if a space have these properties, then we can say that this space is almost close to a big metric space, except having some none of the properties. Okay. Okay. So that's why in the direction we shall first start some problems. Then we shall reveal some important facts. Okay. So let's start. So before that, hold a moment, please. Okay. So the first question is as follows. So first we are going to start with some problems. So the first question, 1 minute, hold on a moment. Let me check everything. Okay. And one more thing, Mustak. In the meantime, if you have any doubt or any query, please unmute yourself and ask me because while teaching, I am unable to see the chat box. So the question is as follows. So the question is let f, comma g from x to y be continuous. Okay. And assume y is how short. Show that all those x's are fx equal to gx is closed in x. So what are the questions? So f is a map from x to y continuous. why house job? Show that all those x for which fx equal to gx, such a set is always closed in x. Try to show this. It is not difficult. Take your time and let me know. In the meantime, let me find some other questions. Mustab, do you have an idea? Okay, please try for a few minutes, then I shall ask. So, Mustab, do you have any idea, or can you tell me how to proceed? Okay, so it seems to be an easy problem, but it seems it's difficult for you. So let me explain. So what do you need to do? That set x as f is equal to gx is closed. Okay. So we are defining function h, but where x to y cross y. How we are defining x goes to first first coordinate fx, second coordinate gx. Okay. Now define now consider diagonal of y. Now consider diagonal of y. which is delta y. This contains y comma y such that y belongs to y. Okay. Now observe that H inverse diagonal of y. This thing is nothing but collection of all those x as that fx equal to gx. Is this clear? H inverse diagonal of y is equal to all those x so that fx equal to gx. Now, why house drop? It is well known. Okay, I mean, it's given. So in this implies diagonal of y is closed. Okay, this implies H inverse diagonal of y is closed as H is continuous. As H is continuous. So this implies what? This implies all those x as an fx equal to gx. This set is closed set. So this is the argument. So let me explain it. What? Sorry. If gx to a continuous is known, and it is given that y is house job, we need to show that all those x such that fx equal to gx is closed. So for that, what we are doing, we are considering a map H from what to have from x to y cross y, sending x to fx comma gx first for fx and border gx. Okay. Now also it is observed that since that we have diagonal of y delta y and it is well known that y house drop implies diagonal of y is closed. And also observe the H inverse diagonal of y. The inverse imaginary diagonal of y under the map H contains all those x's of the fx equal to gx. So this implies what? H is continuous. So H inverse diagonal of y is closed. So this implies that set x subset of fx equal to gx that is closed in closed set. So yeah, so that is the argument. Is it clear? Please let me know. Mustaq, is it clear? Please let me know. Take your time. Please let me know. Okay. So since Mustaq, you did not tell anything regarding the doubt or any probable solution, so I'm assuming that you understand the solution correctly. Okay. So let me go to the next problem. So the next problem is as follows. Let P x to y be a closed continuous surjective map such that P inverse singular y is compact for each y belongs to. Sorry, P x to y continuous surjective maps as a P inverse y surjective map. Okay, surjective continuous surjective. Surjective map. Okay, surjective map show that if x is normal, then y is also normal. So what is the question? Question is that suppose Px to y is a closed continuous surjective map. Show that if x is normal, then y is also normal. Okay. So basically, it's a quite tricky problem. Directly using definition, it cannot be solved possibly. But anyway, first you try. But I shall give some hint. Okay. First try it yourself. I shall wait for a few moments. Please try by yourself first. Do you have any idea how to proceed this problem, or do you have any idea how to start with? Okay, so 1 minute. So, so the hint is as follows: if U is an open set containing P inverse singular Y, show that there exists a neighborhood W of Y such that P inverse is actually. If you open the country P inverse Y, show that there is a neighborhood W of Y as a P inverse W subset of P. So use this hint and then try to prove that. If you get any idea, please let me know. In the meantime, I was somehow trying to figure out how to attack this. Now I've pointed out this can be attacked. So try to figure this out by yourself. Take a few moments. So don't think in the direction of the definition. The hint which I provided, please try to use the hint and try to solve. At least try to attack the problem. Only use the hint. If you start with from from the definition itself, you may start. So the hint I have given, please try to use it in a very clever way. Take your time and let me know. So, Mustaq, are you able to figure out how to approach this problem? Okay, it seems you are, I mean, it seems um, that it has not been done till now. So, 1 minute. Okay, so let me solve this for you. Okay, so there are two steps. First step is to prove the statement using the hint. Second step is to prove the statement itself. Okay, prove the hint itself. Sorry. So solution. What we need to show y is normal. For this, what we need to show, choose to close set, choose to close set A B of y which are disjoint, and we must show there is u v open in y so that u intersection be empty and a subset of u b subset of p, right? So this is what we need to show, correct? Now we are considering ux. So now hold on a moment. Hmm. Hold on a moment, please. Okay, so the solution goes as follows. Since Since okay, so let me write down the solution again. By hint, the hint is true for a single point. Not only that, the hint is true for an open set. So by hint, if P inverse B subset of U for some source of B of Y and some open set W of X, then U of X, then P inverse W subset of U for some neighborhood W Y of B. Okay. Now using this, the solution goes as follows. Using this solution goes as follows. Since points of X are closed, all points in Px are closed. All fibers P inverse Y subset of X are therefore also closed. And let Y1, Y2 be two distinct points in Y. Now, since X is normal, so we can separate the disjoint closed sets P inverse Y1 and P inverse Y2 by disjoint neighborhoods E1 and U2 using the second part of it. So now choose W1 of Y1, a neighborhood, and W2 of Y2, such that P inverse W1 subset of U1, then P inverse W2 subset of U2. Then W1 and W are disjoint. Thus, wise. Hausdorff. And sorry, that's the wise, not Hausdorff. Wise, normal. So, yeah, but please go through the argument once and let me know do you understood it properly or not. The argument is quite long indeed. Please take your time and let me know. I shall back to a few moments. Okay, so is this argument clear to everybody? Mustaq, is the argument clear to you? Okay, I hope it is clear. So let me re-explain the argument, and then we shall move to prove the hints that we have used. Okay, so basically what we have done. So the implication of this hint is that the P inverse B subset of U for some B subset of Y and some opens at U of X, then P inverse W subset U for some neighborhood W of Y of B. Okay, that is the main trick using hint. Okay, now to solve the theorem goes as follows. Since the points of X are closed, all points in Px are closed. Okay, so all fibers P inverse Y subset of X are therefore also closed, and let Y1, Y2 be closed distinct points in Y. Now since Y is normal, we can separate the disjoint closed sets P inverse Y1 and P inverse Y2 by disjoint neighbors U1 and U2. And using so we choose W1, W2, Y1 of Y2, so the P inverse rows of the U1, P inverse was a U2. Then W1, W2 are disjoint. Thus Y is normal. Okay. So this is the argument. So this tells that. So this tells. I mean, so this proves the whole thing. Now we need to prove two things. First of all, the fact that we have used previously, namely this one. 1 minute. Yeah. Yeah. So this fact needs to be proved, and along with that we are going to prove the hint also. Okay, so first let's try to prove the fact that we have used. Okay, yeah, it's a big I mean, so maybe Mustaq is thinking that's a big problem. Yeah, it's right, the problem is quite big enough. So let's move on to solve the hint first. So proof of the fact that we have used. So proof of the fact that we've used. Okay, the point is, for each y belongs to B, it has a neighborhood Wi such that P inverse 0 subset of U. So the union W is equal to union Wi is then a neighborhood of B with P inverse W subset of U. So yeah, so that's what the fact is. Okay. Now prove the hint. So basically, what we have proved in that fact is that for each y belongs to b, by hint we are getting wy, and then w equal to union wy, and this tells the p inverse of sub u. Okay. Now prove the hint. Note that observe p inverse w subset of u. If and only p n belongs to w implies x belongs to u. This holds if and only if x does not belongs to u implies px does not belongs to w. This holds if and only if p of x minus u subset of y minus w. This holds if and only p of x minus u intersection w is equal to empty. Okay. So now each y does not belongs to the closed set p of x minus u, and that is a closed set. Okay. So a whole neighborhood y of y is disjoint from p of x minus u. That is p inverse w subset of u. So that is the hint. So there is nothing to explain much in the hint in reality. Okay. So the hint is that for each y belongs to y, for each y belongs to y, I mean, since P inverse W subset of U, so this tells that Px belongs to W implies X belongs to U. This is equivalent to saying X does not to U implies Px does not to W. This is equivalent to saying that P of X minus U subset of Y minus W. This is equivalent to say P of X minus U intersection W will empty. This tells for each Y belongs to P of X minus U. The whole neighborhood W of Y is disjoint from P of X minus U. That is P of W subset of U. So yeah, so that's the whole argument. So Mustaq, please take your time, go through the argument once. Let me know if you have any question or any doubt. Okay, I shall be back with a few moments. Okay. Okay. So Mustaq, is the argument, full argument clear to you? Please let me know. Okay, I hope so. Now let's go for the next problem. The next problem is as follows. Let P y to x be closed, continuous, surjective map says that P inverse singleton y is compact for each y belongs to y. So if x Hausdorff, then show that P y to x be closed continuous surjective so that P inverse singleton y is compact for each y belongs. If x is Hausdorff, then show that y is also Hausdorff. So, so basically, the hint is try to use the previous hint. Okay, take your time, think about it. I shall be back in a few moments. Yeah. Mustaq, are you able to figure this out? Please let me know. Okay, so it seems that you are able to do it by yourself. So let me solve it. Okay. So it is given that X house drop, and to show Y auto, so choose Y1 Y2 belongs to Y, Y1 not equal to Y. Okay. So by previous hint, we can separate the disjoint spaces P inverse Y1 and P inverse Y2 by disjoint open source U1 containing P inverse Y1 and U2 containing P inverse Y2 of the house of space X. Now choose open set W1 containing Y1 and W2 containing Y2 such that P inverse W1 subscript U1 and P inverse W2 subscript U2. Okay. So then, hold on, but then, so this tells that W1 intersection W2. This tells that Y is a house job. So let me re-explain the argument. Y is house drop. Suppose y and y2 belongs to y and y1 not equal to y2. So by previous hint, we can separate the disjoint spaces P inverse y and P inverse y2 by disjoint open source spaces. Hello, hello, hello. Testing. Hi, sorry. Due to some technical issue, in between a few moments, I could not be able to connect properly. So I say I'll extend the session up to 10 by 10 to 15 minutes. Okay. I'm extremely sorry for the convenience and inconvenience caused by me. Okay. Okay. So please hold a moment. Hmm. So okay. So where are we? Uh, okay. Hmm. So the last question which we were discussing was regarding. So it was that why to house drop or not. Okay. So the argument goes as follows. Since x is house drop, so choose y1 y2 belongs to y and y1 not equal to y2. So by previous unit we can separate the disjoint spaces p inverse 1 p inverse y2 by disjoint open subset e1 subset of p1 and u2 subset of py2 of the house drop of x. Choose open sets w1 subset of y1 w2 subset of y2 such that p inverse w subset u1 and p inverse w2 subset of u2. These implies u w1 it is w2 empty and y is the house drop. Okay. So that is the argument. So this tells that if x is house drop, then y is house drop. Now the question is that show that under the same question show that if x is regular, then y is regular. How to do that? So I mean basically you need to use the previous theorem statements and try to figure it out by yourself. Okay, so that will be nothing complicated, I guess. Please take your time, think about it, let me know what's the. Hmm. So basically, the hint is sorry. Hint is try to use previous solutions. Hint. Try to use this. Take your time. Let me know. Hmm. Take your time. Let me know. You need to only use the hint of previous theorem and actually you can try to prove this using technique that I've done the previous theorem. Okay, please take your time. Let me know. Okay, Pustak. So are you able to figure out how to do this? Okay. So let me write it down. Solution. Why is Hausdorff? By A. But the first one, why is Hausdorff? Okay. Let's see subset of Y be closed house space, and Y belongs to Y. Be a point outside C. It is enough to separate the compact fiber P inverse Y subset of X and the closed set P inverse C subset of X by disjoint open set. So this tells what? This tells each X belongs to P inverse Y can be separated by disjoint open sets from P inverse C since X is regular, right? So this implies what? By compactness of P inverse Y, we obtain disjoint open sets from P inverse C since X is regular and then a disjoint open set U subset of P inverse Y and V sub of P inverse C as required. So, one, hold a moment, please. Let me check everything is going fine or not. So basically, the process is as follows. Y house drop C subset Y be a closed house space and Y belongs to be a point outside C. It is enough to separate the compact fiber P inverse Y substrate with closer P inverse substrate. Each X belongs to P inverse Y can be separated by disjoint open sets from P inverse C. Since X is regular, we compact with the P inverse, so you obtain disjoint open sets of P inverse C since X is regular. These simply U subset P inverse and V subset P inverse C. Okay. So, so that is the argument. So is it clear to you? Mustaq, let me know. Okay. So I hope this argument is clear to you. Now let's go for the next question. This question tells that under the same assumptions, show that if X is second countable, then Y is also second countable. Please take your time and let me know. So the hint is use the previous technique as follows. The hint is the use previous techniques as follows. Sorry, previous techniques as before. Please take your time, let me know. So the argument goes as follows. So Muslim, are you able to figure out how to do this? Okay, so let's try to prove it. Hmm. So let Bj be countable basis for x. For each finite subset J contains it plus let Uj subset of x be the union of all open sets of the form P inverse W, the W subset of U, and P inverse subset of Bj. There, there, there are countably many open sets Uj. The image P of Uj is the union of open sets in Y, hence open. And let now P subset of Y be any open subset, the inverse image P inverse V is equal to Y belongs to V, P inverse Y is a union of fibers. Now since each fiber P inverse Y is compact, so it can be covered by finite union J belongs to J of Y, J of finite union of so let me share the screen. Okay. So let me check whether everything is working properly or not. Sorry for the inconvenience caused by me. It seems there is some error from the software side, which is not in my hand. Okay, let me check everything working properly or not. Okay. Hmm. Okay. So where are we? Okay. So now, since Bj is the basis of the union of Bj is the basis sets contained in P inverse V. So by lemma 2, there is an open set W subset of Y such that P inverse Y subset of P inverse W union J belongs to G of Y Bj. Now taking union of all these open sets W, we get P inverse Y subset of P inverse W, uh, subset of union J. So union J belongs to JY of J. Taking union now, taking union of all these open set W, we get P inverse Y subset of U of JY subset of union of J belongs to JY B of J, which is subset of P inverse of B. Okay, and so then we now have P inverse B is equal to union Y belongs to B U of JY, so that B is equal to P inverse B, which is union Y belongs to V P U G of Y, and this is the union of sets from the countable collection P of Uj of open sets. Thus, Y is second countable. So that is the full argument. So, hmm. So So let me repeat the argument once. Okay. So here, what we need to prove? Prove that x is same countable, then y is also same countable. Okay. And we need to use a previous technique before. Let bj be the countable basis for x. For each finite subset j subset of j, let uj subset of x be the union of all open sets of the form P inverse W, with W subset of y and P inverse W subset of bj, j belongs to j. And there are countably many open sets uj such that the image P of uj is the union of open sets in y, hence open. Now let V subset of Y be any open subspace. The inverse image P inverse V is equal to union of Y belongs to V. P inverse Y is a union of fibers. Since each fibers P inverse Y is compact, it can be covered by finite union J belongs JY Bj of basis set contained in P inverse V. By lemma 2, there exists an open set W subset of Y such that P inverse Y subset of P inverse W subset of union of Bj. Now we are taking the union of all these open sets W, and we are getting P inverse Y subset of P inverse W subset of union of Bj. Now taking union of all these open sets W, we get what? We get P inverse Y subset of union of Jy subset of UjBj. Now P inverse V, which is union of y belongs to be ujy. So V is equal to P of P inverse V is equal to union of P of G of y is the union of the sets of the form of countable collection P of uj. So this tells that y is second countable. Is the argument clear? Let me know. So basically, this is doing what? First, we're considering the countable collection open sets. Hold a moment, please. Okay. First, we're considering the physical countable collection of open sets. Okay. Now we are basically taking the intersection and union in a nice way such that our condition is getting satisfied. So there is nothing big thing doing here. We are basically doing the obvious thing, but very technical way. Okay. Is the argument clear to everybody? Okay. Okay. Please let me. Okay. Now, the next question is as follow. Hold a moment, please. Okay. Mm. So, next question is as follows. If Y is compact, then the projection map by 2 from X cross Y to Y is perfect. How to do that? Perfect means closed image of convert closed set is closed. Okay. So, Voice comparison projection is perfect. How to do that is what to that is we what we need to show. We basically need to show is that pi to inverse y is compact for all y belongs to. It's a homework. So please think about it in your home. So so this is nothing. I mean, there is nothing to in reality to do. Okay, it is very easy thing to do by yourself. Okay, so let's end here. If you have any doubt or any question, please drop an email. I shall definitely get back to you as soon as possible. So we shall meet on the next Friday, the fourth live session, 7 to 9 p.m. Okay. Thank you. Bye.